All right, so how you guys doing today? It's going okay? Perfect. Thank you, I'm good. So, like I said on the Wednesday lecture, I'm going to move on to the IR spectroscopy today. I just want to make one point of the previous lecture is this one. Okay. So, if you have the mass spec electron bombardments on certain carbonate compounds, you can definitely have certain two possible scenarios. One of them was this one that I taught on Wednesday. This would happen. Okay. So basically what happened to this one is they're going to lose this part. This is what I explained last time. So that means they're going to have certain, this one is actually came from right here. This part will become right here, so become this one. So this, the have electron goes to pick up the hydrogen over here. So this is why you're actually going to see hydrogen screw over here, and then this just stayed there. But when it breaks, it has the pair of electron donated here with this carbon with those two. Yeah, so this part I did, but make sure you guys get this one right too. But most importantly, this is what we call McLaughlin rearrangement. Okay. What's that sound? So anyway, so the most important thing was this one that I focused on this one too much last time. I didn't finish this one, but this is the one that you lose. So that's why you're only going to detect certain part of it. But to be honest, I don't know if you watched the Wednesday lecture on YouTube. I only focus on the upper cleavage, which is the one you would like to see. You will see on the exam. But this one, I really don't think so. But still important information, so I just did it again. But also make sure you go over other the practical problem I went over on Wednesday. So anyway, so let's move on to the IR spectroscopy. So whenever you talk about the IR, infrared, right over here, spectroscopy. So once again, we try to find out the information of the compounds by looking at the interaction between the compound and the light, or we can say energy more specifically, but in this case, obviously it's pretty much one type of light. Okay, so whenever you do this, what we need to know is this is something we learned in the previous chemistry course. This is the speed of light. This is the wavelength, and this is the frequency. I'm not going to go in much detail because I already did it on Wednesday. Make sure this is a good reminder for whenever you look at the sample of IR spectrum in chapter 12. So if you have this one here, this main point was it's actually this one. So once again, you guys remember this hopefully from Zenchem 1 and 2 and Auger 1 obviously. That we believe that the energy, even that in form of the light, are quantized too. So meaning they're actually going to have a certain type of a discontinuous metal-like property are there. So that means whenever actually you look at some molecules here and where the compound it is, we're actually giving you certain numbers for bond length, whether it's triple bond, single bond, or double bond, so forth. They have a certain length of their distance between these two nucleus. But to be honest, all the molecules are always moving, like with the neighboring elements around it too. So what they normally do is they do like a symmetric stretching or asymmetric stretching. They can also do bend on the same plane or outer bending. Or they can also sometimes do weird twisting as well too. So the point is the molecule doesn't really stand still in the space. well, they're actually going to interact quite well and also kind of vibrates over all the atoms in the compounds. That's why they're going to have certain weird motion like a bending, stretching, and twisting, and all sort of that. Okay, makes sense, right? So far, we're good. So if that is true, if those type of the frequency of the vibration matches up with the frequency of the certain electromagnetic radiation. So the light is simply what? Electromagnetic radiation. Meaning they're going to oscillate the electrical field and magnetic field perpendicularly together at the same time, so it can travel through the space. And this is how we deliver the energy into the compound, meaning in form of a light. Okay? So this is why whenever the light comes to the compounds, if that certain light at a certain wavelengths, meaning certain frequency as well. If that frequency of the light is correspond to the frequency of the vibration and thus the motion in the compound, they would absorb that light into themselves, so they can do the motion even more vigorously. Okay, so if that happens, what happens to this one is whenever you shoot the light and the different wavelengths or frequency in the certain range of the what? Infrared. It's in the between near infrared or far infrared, in the middle. This is the perfect one. So when it happens to the compound, they're going to observe the certain IR at a certain frequency, or you can say wavelength, and they'll show you some observance or not so much observance and so forth over there. Okay, so we're gonna call this absorption spectrum. Okay. So spectrum simply means it's the range of the light, right? Especially focus on the IR. But when it go passing through the compounds, they only going to observe the certain the light in the IR at the certain the wavelengths or the frequency, you can say, because of their each different each elements, like here, and so forth, they're going to show different frequency of their vibrations. So each different functional groups or each different bonding will try to observe the light at a certain specific different light at the frequency. Or you can say wavelengths, it's the same thing, but it's just inversely proportional. But makes sense, right? Do you have any question? It's good. Oh, perfect. Thank you. So if that is true, so the ion spectrum, so mass spec is more like you're trying to find out the molecular size, molecular weight, and possibly if you're lucky, you can have some structural ideas and also the formula, chemical formula too. But ion is more focused on the what function group it has. So it's not really good ideal instrument to detect its structure or what's the interaction between carbon and hydrogen, but it would be more like what kind of functional group does this compound carry, so it gives certain unique physical or chemical property of the compound. That's the thing we mostly look at from the IR spectrum here. So to get to there are certain things I need to go over. So like I said, there will be such a range of the light, but we're actually going to put it in the unit of centimeter and power by -1. So because we're going to do this, because we're going to have a x-axis for weight number. Weight number. The weight number is like you have the nu, right, in the frequency with the bit of a weird slice on the top, and that is equal to 1 over wavelength in centimeter. So this is a reciprocal form of the wavelengths that is in centimeter, not meter. Okay, so it's just the wavelengths, but in a reciprocal form. So you can put it in the weight number in this way. This is somewhat like your frequency, but in different form. So we have this symbol right there to represent your weight number. And weight number usually range from 4,000 to 400. Okay, so because this is the range that we can find the more useful absorption of the light of the compound, so you can analyze the absorption spectrum to see what functional group it does really have on this spectrum. Okay, so I'm gonna. Here's the thing. Unlike the mass spec or the NMR we're gonna do next week, this is kind of a this is also spectroscopy, means you're only going to see the relative amount of the absorption of the light, but it's not specific on the certain functional group, meaning it depends on the where it attached to. So if it's attached to the, for example, carboxylic groups, carboxylic groups, like even though it's the same hydroxyl group, if it's attached to the carboxylic group, or if it's attached to just the alkane or something, they also show the change in the location, but it's in the bit of a certain range, but it's not so much a difference, but in a particular range of the spectrum will be slightly different. Okay, this might be the dramatic one actually, but so that means I'm not going to ask you to memorize where does the absorption peak is there to find out which group it indicates. You don't have to memorize, because I'm gonna put the table I'm gonna put the table on the exam and the quiz. So you don't have to memorize all, but I just want you to know how to use them. I'm gonna show you a certain example here. So on your exam, on the quiz, you're gonna have some of the table indicate what wave number, what kind of a function group you're supposed to find in that peak, and then so forth. So don't memorize them, but just know how to use them, so you can tell, oh, if this is the right compound or wrong compound, this might be this compound and this based on this R spectrum, so forth. They'll be all good enough. So it won't be, I believe it won't be too hard, because you have all the information given to your exam or the quiz. You just need to analyze them in a certain way, and then you can find a pretty easy pick from the multiple choice questions. Okay, sounds good, right? Good, perfect. So, but basically, there are only a couple of things that I kind of want you to know from just analyzing your IR spectrum here. So, like I said, this is so this is the wave number. Okay, once again, wave number. Okay, number. So the Y is the what we call transmittance, or you can say transmission. It doesn't matter. Okay, both are the pretty much the same, because whenever you shoot the IR onto the sample, the one thing that you need to know is unlike other graph that all starts from the bottom, right? But in this one, you actually start from the 100%. So this is your set from the bottom. This is kind of weird, because the 100% means whenever you shoot the light through the compounds, all the lights that wave number passes all of them just pass through. So the detector catches almost 100% of the incident light from the beginning to there. So meaning it's all passed. All of the light just passed through the compound. Nothing was absorbed to the compounds. Okay, so this is why this is our actual start point, not here. This Y is actually transmission and percent units. Okay, makes sense, right? So the couple things that I want you to know is this type of things. So whenever you have a 4,000, you have a 3,000, 2,000, 1,500, and so forth. It'll be 400 over here. And here, this is where we call fingerprint reason. Okay. This is where you're gonna find some carbon, nitrogen, carbon, oxygen, and other halogen over here. So this is where you're gonna see some absorption spectrum from 1,500 to 400, which is the right side of the IR spectrum. You don't really have to worry about this one too much because obviously you're gonna have some table over there, but we call this fingerprint region because if you have a similar absorption spectrum pattern on here, one to another, that means they're most likely they're going to be same compound. This is why we call this fingerprint. If that shows the same, that means those two compounds should be almost 99% same. So normally this is just something that you only need to know, but not a lot. Okay. But for this one, so this is about 2800, like somewhere or in 70. Like I said, there's no like a defined like a range for anything to separate the groups that you want to identify aside, because like I said, all the functional group absorption may be shaped a little bit different among different types of compounds anyway. So this is where you can normally find this one. Those type of bonding over here, okay? And this is where you can find some triple bond, okay? Carbon, nitrogen over here, okay? And you can also find some double bond here, which is carbon, oxygen, nitrogen, and carbon over here, okay? This is kind of something you can do, okay? So whenever you have this type of information over here, what you can normally do, so what you can normally do is let me give you one example over here. So let's try to do hexane. Okay. So hexane will be just the CH, most of just a CH and CH. So this is very simple. If you do this one in this way, you're going to have this type of peak, this one, because the only thing that you have is over here. Okay, so this is why you're gonna see some the kind of very simple absorption spectrum for hexane over here. Okay, but if you do change this one to hexene, okay, hexene, meaning there is a double bond on the first and second carbon, you're going to have a little bit of a sign of this one that also indicates the carbon hydrogen. For sure, this is where you can have a carbon hydrogen bond absorption, right? But from the double bond, one of the carbon is the double bond that shows this one over here. Okay, and also if that is true, you also see the right? Yeah. Then if you do this, you have also carbon-carbon double bond here, and this is that means you're also going to have some peak. Unlike the hexane, there's some air between these two. We have some peak over there as well. Okay, and also, like I said, fingerprint region is the kind of a very essential part to identify your compounds to another. This will be also different pattern here. It won't be like same as the hexane, but also change. But you have to know for real because you just need to they're different because they're different compounds. They won't be same. But the most important, you have the one on here, it's written here. This is slightly higher than 3,000. But once again, you don't have to memorize it. It's okay. I just want you to tell you because they will be all on the table, so you don't have to memorize them. But I just want you to know if there's the double bond between carbon. Because of the carbon that also has the hydrogen bond, you'll see the change in that peak from the hexane. And obviously this is a carbon-carbon region where you can set some absorption over too. So there'll be some over there. And you don't have to much worry about this one, but it'll be different from hexane as well, okay? Make sense, right? You good? Okay, perfect. So if that is let's just do one more, okay? So maybe you can do the hexane over. So it is triple now, okay? So if that is the case, also again, you just need to go ahead and find your table in your exam. And you're just gonna see another peak of this one. This is about 3,000 3300, okay? But it's on the table, don't worry about it. So you'll see this one too, because it's a triple bond to another carbon with the hydrogen. So it's still this plan with these two, but this is what it looks like in the hexane. And then obviously now you're going to have some, not here, right? Because it's not double bond, it's not a triple bond, but we have some here. It's about 2200 here. And it's usually very strong, even stronger than double bond attraction. So you don't have much of the peak here, but also this region will be different from other hexane or hexene for hexane. Okay, so this is a very obvious example you can analyze by using just simple, like somewhat accurate separation of the location we can find the fluorescence peak from the IR spectrum. Okay. Kind of makes sense. You good, right? Okay, perfect. So, if that is the case, I mean, I don't think this is too much to memorize, but anyway, I'm gonna put the table, so don't memorize. I mean, it would be great if you memorize them, but you don't have to, okay? So maybe on the exam, maybe I can give you one example. If you have compounds, okay, this one, okay, you have a compounds looks like this one. The everything will be on the table. The only thing you have to know is, oh, this is where you have the carbonyl groups, okay, which is about 1700 over here. You have, but hydrox group on here particularly, usually we're about 3500 here. So for example, if I give you the spectrum like this, right? And then there will be the double one here, something like here. You may confuse with these two because the double bond and the carbonyl groups usually lay in the about similar region here. So you may confuse because it's really hard to tell. But for this one, it's obvious it has to be this one. So if this one still you can tell, oh, slightly different, right? But it's very confusing. If you sum it here, I mean, you can say if it's carbonyl peak or the double bond peak. It's confusing, but obvious the OH group that you can only find on the 50-100 peak over here. Then you can say, oh, it gotta be, if it's A and B, your choice, B should be the right one for this one. It will be very straightforward. Okay, so don't worry about too much. The table also will be given here. So I mean, you know, there's nothing really you need to worry about. Just need to know how to use the table, which will be what wave number, what function group you're supposed to see, and just use that knowledge to find out which might be the right compound that went through with the IR spectrum over here. Are we good? Yeah, go ahead.
So how would that question exactly be asked?
Yeah, so this is one possible exam problem. So I give you like two compounds, so you can look at the structure, right? And you have a table that says what function group in where in the wavelengths, right? And then I'll show you the spectrum, and you see because of this, the compound is this one. That would be your exam.
So the table's gonna have like
numbers.
The numbers on the bottom?
Absolutely.
Okay.
So you don't have to memorize it. You just need to know where the peaks are, to find it, and you need to look at it from the structure of your samples. You can find it. And maybe you can, yeah, that's pretty much it. And here's another thing. I hope if you watch this from the YouTube channel, this very carefully. I don't know if you already did the lab 1. Not yet, okay. So group A did the synthesis of the aspirin, which is acetylsalicylic acid. That will be on the exam, for sure. So I'm gonna put the spectrum of that one. All you need to know is, that is that compound. And what group, what spectrum. So if it is OH, will mean something. So I'm not gonna lie, really, I'm gonna put that as the salicylic aspirin on the as example. And then the only one thing that I want you to remember is once again, that the hydroxy group that specifically attached to this, the carbonyl group makes the carboxylic acid group right here, carbonyl group here, right? That is one part of your, that is one part of the aspirin. Then this OH hydroxy group normally range in the somewhere between 4,000 and 3,000. But for this specific case, for this carboxyl group and OH, usually weigh about 2,800. That's quite of a very unique difference. So I want you to remember this one. So for aspirin spectrum, also I'm going to show you in the lab too, because we're going to do the IF in the lab, and this week and next week. You're going to see the OH group not here, but here. And that is for sure, because it's just the aspirin group. It actually makes sense. So like I said, there will be certain same functional group lays in the different wave number, but similar, not too far away from each other. But because of this, the structure may change the position, but it will be all in the, it will be still anyway in the table, so don't worry about it. But I think it's better if you put the certain compound we already run in the experiments, will be more good candidate molecule for the exam. Make sense, right? Perfect. All right, you guys doing great so far. That's very nice. So, all right. So I'm gonna just move on to the next chapter. This is what we call nuclear magnetic resonance spectroscopy. Okay. So we call this NMR, because of what it says in the term. So we call this nuclear magnetic resonance, means how we analyze the compound. So NMR is used for how does the carbon and hydrogen are aligned in the structure. So most of the time, most of the chemists will use NMR first, because this is the one that they can get a lot more about the information about the structure. So this is the one that use most of their organic chemical experiment. As you can think of, the organic compound is mainly made of carbon and hydrogen. So this is why when you look at the NMR, they use either proton or carbon-13 NMR. Because we have other elements to detect with the NMR, but we use these two because those one has to have either odd numbers, proton, or odd numbers of neutron, either way. So that means if there's a certain element that has even numbers of protons and neutrons, it cannot be used for NMR. Okay. For example, carbon-12, it has obviously its atomic number 6, means 6 protons, right? But this is an atomic mass number, which is 12, so it has to be also 6 neutron over there, meaning it all has even numbers of protons and neutrons, so it cannot be used for NMR spectrum. But only the carbon-13 that can be used for this NMR analysis. Or I mean, hydrogen is a pretty good one. It's 1 proton, makes a perfect example for sample for the NMR. So the reason why we cannot use the one that has even numbered proton and neutron because in this NMR process, we use okay, let me go back to actually before. So you guys remember the atomic structure, right? So you have a nucleus at the bottom, at the center, and it's made of the protons and neutrons, right? And you have electrons just moving in the orbits in the Bohr-Molr, but more specifically, technically speaking, in orbital, right? So then we actually think this is nucleus, right? This is electron. Do you know electron has also magnetic spin, right? You guys remember these quantum numbers? We also know that it also do some magnetic spin or magnetic property on the nucleus because this is also positively charged. So magnetic field, by its definition, that has a certain vector field generated from the motion of your charged molecular atoms. So even though it stands still, there's no magnetic field generated. But if it's spinning, that means that motion of the spin, that the charge, like electron spin, like magnetic spin, like electron, also nucleus can make some small, actually relatively very small, like a magnetic field around it, this one over here. But if that is even, they actually kind of cancel each other. So either proton or neutron are like even numbers. The magnetic spin maybe just cancel them in the opposite spinning, so they can be canceled. But if it's not, they will have a certain direction of the spin in more favor because the odd number, it can be canceled evenly. So they will have certain magnetic moments there. So this is the one that we're going to use for NMR. That's why only carbon 13, not carbon 12, will be used, okay? Or the hydrogen, okay? Does it make sense? Okay. All right. So what happens to this one is whenever you have the nuclears are kind of having magnetic field, magnetic motions there over here. But what we normally do in NMR is we try to apply the external magnetic field using strong magnets. Okay. We call this B naught. So it's external, like we make the strong magnetic field into the sample, and then what they normally do is two things. They try to do the parallel position first. So once they are randomly just spinning in all the random directions, but after you apply the magnetic field there, they're either going to go align parallelly, so they're also heading the same directions, okay? But some actually do anti-parallel position over there, okay? So obviously, the one that has the parallel position to the external magnetic field direction will be slightly more stable, because this one is the one that goes against it, right? So they're gonna show you the certain directions, but it could go in the parallel or anti-parallel. There will be slight difference in energy, because those are the ones are more stable. Those are the ones it will be more unstable. Okay, so if either they wants to go up to this spin, so we actually call this alpha and beta spin. You don't have to know, but if they go to the spin inversion down to here, this is a more stable form, right? This is a more unstable form. So you need to give some the energy to the ones on the parallel position to make this goes to the anti position. So they need to have the energy to go to this spin. And when this spin goes down to the parallel spin, they emit the energy. Because the unstable now, they're more stable now. To be stabilized, they need to emit the energy. And those the energy, we call this radio frequency radiation. So whenever you have so normally what we can do with this magnetic field, they can put it up to very strong magnetic field up to 21 Tesla, but they normally adjust it from the 4.7 to 7 Tesla, which is good enough for our NMR testing. But the point is, whenever they increase the external magnetic field, the gap between these two will be obviously, we can say it's delta E, because there's this energy gap there between this the alpha and beta spin. So if you increase the strength of the magnetic field, external magnetic field, the gap between these two will be bigger and bigger. Obviously, right? If it's a bit more strong, a bit more instability will be happening to this beta spin ones. That's why you have more energy to make it even get to the much unstable, much higher energy state, or if you make it down to the stable, it has to lose a lot more energy to it. Okay? So whenever you do put some energy in form of RF, radio frequency, they can be into the same spin with them, and they become in the resonance positions with them. Then we try to detect those signals, so we can tell how does the hydrogen or the carbon will interact with the neighboring atoms in here. I'll stop here today, but this might be the first time for you. We're in group B on Friday, so we're gonna have some time for extra credit. Okay, so yeah.